Good morning, Algebra 2 students. Hopefully you're having a great day so far. Today we are officially going to start our second unit of Algebra 2 talking about simplifying radicals. I know at least the beginning of this stuff you probably have done in Algebra 1 or geometry before, but I promise, so that may be a little bit of a review, and that'll be good because it'll kind of refresh your memory on this stuff. But I promise the later stuff that we do will be brand new, and it will be pretty much taking this idea of simplifying radical expressions and expanding upon it. Okay, and expanding upon it. So normally when we deal with simplifying radicals in a typical year, the 2020 is anything but a typical year. In a typical year, we deal with square roots, cube roots, and fourth roots when simplifying radicals. Being that this is sort of a off year, we are in this unit only going to be talking about square roots. So whether or not you find yourself lucky and that's fewer information, a little bit less information you need to know, then good on you. But if you are curious on how cube roots and fourth roots would sort of fit into this concept, it's very similar, and I'd be happy to show you separately. So just let me know, and I'd be happy to do that for you. But when we're dealing with simplifying radicals, we are dealing with the square roots. In this particular year, the square root symbol you all know looks like this. Okay? And just to give you a quick example, you know at this point that the square root of 25 would equal 5 because the way that the square root works is that it pretty much is asking the question of what number times itself is equal to this number underneath this radical symbol, and we would know that that's equal to 5. So the square root of 25 is equal to 5 because 5 times 5 is 25. So if we are going to simplify more complicated expressions involving square roots, it's probably a good idea to have a good handle on our perfect squares. And by perfect squares, I mean this list of numbers that represents numbers that have simple square roots, numbers that have integer answers as their square roots. Okay? So consider something like this. If I have 0, 0 squared is 0. If I have 1, 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. You may have already known those. 8 squared is 64. 9 squared is 81. 10 squared is 100. Typically that's like all students are pretty comfortable with that, and then they're like, ooh, 11 squared is 121. 12 squared is 144. 13 squared, 169, 14 squared, 196, and 15 squared is 225. So that is what you are expected to know in this class in Algebra 2 CP. You may have had a good grasp up until maybe 10, 11, and 12. Some students kind of forget these last couple, but commit these to memory. These are your list of perfect squares. Okay? And they're called perfect squares because of a couple of reasons. Number one, because you can create squares with this many blocks of things. That's why they're actually called squares. So I could create a 1 by 1 square, which is 1 squared is 1. I could create a 2 by 2 square, which is 2 squared, or 4. Notice that that would take 4 blocks to do. A 3 by 3 square is 3 squared, which takes 9 blocks to complete, and so on, right? I'll do one more. 4 squared would be 16 blocks, right? 4 squared. So maybe you learned something just now. That's why they are actually called squares, and why raising something to the second power is called squaring it, because you're essentially taking this number and creating this geometric square. But the reason why, another reason why they're called perfect squares is because algebraically, if you take the square root of any of these numbers, it results in an integer. And it's very easy, right? If I said, what's the square root of 49? Well, 7. You know, you don't have to, there's no work to do. There's no real thinking. You can, of course, use a calculator if you forget your perfect squares, but for the most part, you'd be able to look at that and say, oh, the square root of 49 is 7. But what about any number that's not on this perfect square list? Well, a lot of them are decimals, right? Like take the square root of 11, for example. The square root of 11 is not a perfect square, it's a decimal, right? But instead of dealing with those decimals, we are going to learn some strategies now to actually rewrite those numbers in easier ways to deal with. Okay, rewrite those numbers in easier forms. Let me show you an example. Okay, how about something like the square root of 20? Okay. Clearly, the square root of 20, not a perfect square. It's not on our list here. All right. But we can try to break down the square root of 20. And you could recognize that, ooh, the square root of 20 actually has a perfect square factor. And by factor, I mean numbers that multiply together to equal 20. Isn't it true that the square root of 20 could be rewritten as the square root of 4 times 5? Right? Could I not rewrite this as the square root of 4 times the square root of 5? Because the square root of 4 times the square root of 5 would equal the square root of 20. And the square root of 4 is something that I know. The square root of 4 is 2. So I can rewrite the square root of 20 as 2 radical 5, or 2 square root of 5. You often heard that read as 2 rad 5 is the way it's often said. You could also say it as 2 square root of 5, all those types of things. Okay? And so this is a much cleaner way to write the square root of 20 rather than using a decimal. And in general, when we're dealing with trying to break down any number like this, what we want to do is we want to find the largest perfect square factor of a particular number and break that number down into its factors. Okay, so when dealing with something like the square root of 20, I think to myself, what's the biggest perfect square that goes into 20? Because a perfect square will allow me to get this integer component here. Well, the square root of 4 times the square root of 5 would be 20. And the square root of 4, I know. The square root of 4 is 2, so I can rewrite the square root of 20 as 2 square root of 5. Okay? Notice it would not be beneficial to do this. It would not be beneficial to say the square root of 20 is equal to the square root of 2 times the square root of 10. Right? Even though that is a true statement, neither 2 nor 10 are perfect squares. So this doesn't really get us anywhere. It's like, yes, this is true, and that's all well and good, and congratulations, but this doesn't really get us to any point, right? We can't take the square root of 10 because it's a decimal. The square root of 2 is also a decimal. It doesn't help us rewrite it in a simpler way, all right? So I would not choose to do that. I would instead say the square root of 20 is square root of 4 times square root of 5. This I like. Because again, breaking it down in that way allows us to use this perfect square right there and say, oh, we can rewrite that in a cleaner way. All right, let's take a look at another one. Ready? How about the square root of 90? Okay. Well, the square root of 90, it is true that I could write this as, the square root of 30 times the square root of 3. But 30 and 3 are not perfect squares. Even though 30 times 3 is 90, and that is a true statement, it doesn't help us. What does help us is trying to find the biggest perfect square on this list that goes into 90, and that would be the square root of 9 times the square root of 10. Okay? The square root of 9 is 3. We know that, right? Square root of 9 is 3. So we can rewrite the square root of 90 as 3 rad 10. Does that make sense to everybody? Hopefully. Pretty good with that? All right. One more thing, or one more example. Ready? How about the square root of 27? And let's actually do negative 2 times the square root of 27. Oh boy. Throwing a number on the outside. Negative 2 times the square root of 27. What do? Do I panic? Do I freak out? No. We can simplify the square root of 27. We know that the biggest perfect square is 9 and 3. And this negative 2 is just going to kind of hang out on the outside here. The square root of 9 is 3, so I get negative 2 times 3 times the square root of 3. And then I just multiply the numbers on the outside. Negative 2 times 3 is negative 6, square root of 3. So an easier way to write negative 2 times the square root of 27 is negative 6 times the square root of 3. Alrighty, Hopefully that makes sense. Let me show you one more, and then I'll just talk about a couple little tips, and then we'll go into adding and subtracting. Ready? So one more. How about the square root of 48? All right, square root of 48. Well, yes, it is true that you could say the square root of 48 breaks down to the square root of 4 times the square root of 12, and that is true. However, the square root of 4 is not the largest perfect square, and therefore you'd have this radical 12 left over that you could then simplify again. You'd have to simplify it again. So by not picking the largest one, it creates more work for yourself. Instead, go through this list and think of what's the biggest perfect square factor that goes into 48. The biggest one is 16. I would break down the square root of 48 to be the square root of 16 times the square root of 3, because 16 times 3 is 48. And the square root of 16 is 4, so we end up with 4 rad 3. All right. Notice if we didn't do that, right? If I did this, like I said before, square root of 4, square root of 12, perfectly valid, nothing wrong with it. But notice now I can break down the square root of 12 again, and I would have to say this is 2 times square root of 4 times square root of 3, because 12 has a perfect square factor of 4. The square root of 4 is 2, so I'd get 2 times the square root of 3, or 4 radical 3. Same answer, but notice how much more work was involved when we did not choose the largest perfect square factor. Okay? Notice how much more work. So we always want to try to find that biggest perfect square factor. Now, what if you're dealing with a number that you're unfamiliar with, right? What if you're dealing with some number and you don't know what the biggest perfect square factor is of that number? Well, that's where we have these handy dandy things, calculators, that can help us out quite a bit, right? So what if I have, I don't know, something like this, right? What if I have the square root of 320, right? And I'm asking you to break that down. What's the biggest perfect square factor? Well, you might not know off the top of your head what the biggest perfect square factor of 320 is. If you did, that would be pretty cool. So what you could do is you could use your handy dandy calculator, and you could kind of figure it out. You could go down the list, maybe starting at 225 and say, or 225 is actually too big because 225 times 2 is already exceeding 320. So maybe let's start at 196 and find out if they divide evenly. So I could say, well, what's 320 divided by 196? Does that go in evenly? No. How about the next one? 169. 320 divided by 169. Does that go in evenly? No. Next one. 320 divided by 144. Does that go in evenly? No. Let's try the next one. 320. It's a little tedious, but divided by 121? Nope. 320 divided by 100? Well, obviously not work. We actually don't even need to check that, right? Divided by 100 will give you definitely a decimal. So let's go down to 81. That'll give us a decimal. 320 divided by 64. Oh, we found one. 320 divided by 64 is 5. So now we can break down the square root of 320 into the square root of 64 times the square root of 5. So that's how you can approach those larger numbers that you may not be super comfortable with, is you can use a calculator to figure out, oh, what is the biggest perfect square that does in fact divide evenly? Okay, square root of 64 is 8, so you can rewrite this as 8 rad 5. Okay? I just wanted to make sure I pointed that out to you. All right? And like I said, any number on the outside over here, we just go ahead and attach, just to show you one more of those. If I had, don't freak out because we're going to throw a fraction there, 1/2 times the square root of 80, right? Let's just break down the square root of 80. The 1/2 is going to stay on the outside for a little bit. The biggest perfect square factor for 80 is 16. Because yes, you could use 4 and 20, but then you'll have to break down 20 again. Notice we broke down 20 again up here. So sticking with 16 will help us out a lot. That'll give us 1/2 times 4. The square root of 16 is 4 times the square root of 5. And half of 4 is 2. So you get 2 rad 5. Alrighty. Ooh, kind of cool. It's the same exact thing as the square root of 20 is half of the square root of 80. Wow, super cool. Super cool. All right, so We can deal with these breaking down radicals all day. Like I said, this is probably stuff that you have done in the past where you simplified radicals like this. But what I want to show you now is what if you have multiple, kind of adding and subtracting them all together. All right. What if I have this? Ready? I want to now add and subtract radicals. Okay? Well, adding and subtracting radicals kind of works similarly to combining like terms, which is like a common expression that we use in algebra all the time. Okay? But instead, we combine like radicals. So in that respect, the radical is almost treated like a variable in the sense that if we have 2x plus 3x, that would make 5x. Likewise, if I have 2 square roots of 2 plus 8 square roots of 2, that would make 10 square roots of 2. Those constants get added together. Let me show you a couple of examples. Something like this. If I had 2 square roots of 3 plus 8 square roots of 3, well, that's going to total, like I just said, 10 square roots of 3. Okay, because 2 of these plus 8 more of these would equal 10 of those, right? 2 square roots of 3 plus 8 more square roots of 3 equals 10 square roots of 3. Okay, likewise, work with subtraction as well. If I had 6 square roots of 5 minus 4 square roots of 5, we would get that this is equal to 2 square roots of 5, right? I started with 6. I took away 4, I now have 2 square roots of 5. Okay? If radicals are unlike, radicals cannot be combined together if they are unlike. So for example, 2 square root of 5 plus 5 square roots of 2, these radical components, notice, are not the same. So there's no way to simplify that. It would be like if I had 2x plus 5y. And you'd be like, well, that's really all you can do, right? This cannot be simplified. All right? So like radicals can be combined together, like through addition and subtraction, much in the same way that you would combine variables. If you had 6x minus 4x, you would write 2x, because you had 6 x's minus 4 x's makes 2 x's. Well, same way, 6 square roots of 5 minus 4 square roots of 5 makes 2 square roots of 5. All right? So it's good to know that that works kind of just like combining like terms. But now, let's take it one step beyond. Okay? How about this example? 3 square root of 32. I'm asking you to simplify this completely. Minus 5 square root of 8. Love this example because at first glance, you would look at a problem like that, and if you're asked to simplify, you'd be like, Mr. Giorgio, what are you talking about? You just said I can't combine radicals if they're different, so how could you possibly expect me to simplify that? And then you might think to yourself, wait a minute, we just learned about simplifying radicals. Maybe I can work with the square root of 32 and the square root of 8 and try to break them down, and absolutely I can. All right, let's try to break down this first term here. This coefficient of 3 is just going to linger on the outside for now. The square root of 32, what's the biggest perfect square factor that goes into 32? It's 16, because 16 times 2 makes 32, right? The square root of 16 is 4, so I get 3 times 4 times the square root of 2. 3 times 4 is 12, so I get 12 square root of 2. Interesting. Okay, so we can rewrite 3 square root of 32 as 12 radical 2. Good to know. Good to know. How about this one? I can break down 5 square root of 8 to be, well, let's carry down this minus sign. So minus, just going to carry straight down. Square root of 8 can be broken down. Let's see, biggest perfect square that goes into 8 is 4 and 2, because 4 times 2 is 8, right? 4 is on our perfect squares list. Always look back at that list. Square root of 4 is 2, so I get 5 times 2 times the square root of 2. So I can rewrite 5 square root of 8 as 10 square root of 2. Ooh, and now you look at this and you'd be like, whoa, it's like it's like one of those moments in math where you get that like tingly feeling inside of you and you're like, whoa, I must be doing something right because now, look, I have 12 square roots of 2. Oh, this bell is getting annoying. 12 square roots of 2, take away 10 square roots of 2. I apologize for that in the background. We get 2 square roots of 2. So 2 like terms that were really hiding out in disguise the whole time. That's really what was going on in this problem. There were like terms in disguise. I always call these problems transformer problems because they're exactly that. Like terms in disguise. Yes, I did that on camera. That's exactly what we get here. Like terms in disguise. They don't look like it, but then when you simplify them and work them out, bam, like terms in disguise. All right, let's do maybe 1 or 2 more, and then I'm going to ask you guys to try a bunch on your own for some practice, okay? How about this? Ready? -3 times the square root of 48. Oh boy. Plus 10 square root of 3 plus the square root of 75. Okay? How about something like that? Right? Well, again, they don't look like terms at all when you start with a problem like this, but you might think to yourself, let's see, if we can simplify somehow the square root of 48, the square root of 75, maybe we can kind of get somewhere, right? This -3 is going to linger over here as we try to simplify this first term. We did the square root of 48 on the other side of this page, right? We did it right down here. Square root of 48 is 16, square root of 16 times square root of 3, which is 4 rad 3. So we can just jump kind of right to that right away. Nice that we don't have to reinvent the wheel, right? We get -3 times 4, because the square root of 16 is 4, times the square root of 3, or in other words, -12 rad 3. Next, we have 10 square root of 3. Well, 10 square root of 3 cannot be simplified, right? Radical 3 is already as simple as it can get, so it's just going to carry straight down. And next, we have the square root of 75. What's the biggest perfect square factor that goes into 75 is 25, right? Because we have the square root of 25 times the square root of 3. The square root of 25 is 5, so I get 5 radical 3. I'll just rewrite that down here so it's in line with everything else. And now, take a look. We got -12 square roots of 3 plus 10 square roots of 3 plus 5 square roots of 3. Like I said, like terms in disguise. All together, put them together. I have way too much fun with that. We get 3 radical 3. Because we have 3 square roots of 3 altogether. -12 of them plus 10 of them makes -2 of them plus 5 of them makes 3. Okay? All right, let me show you one more, and then we'll wrap it up for the day. Okay? One more. How about this? Don't freak out because you see a fraction. We got 1/3 times the square root of 72 minus the square root of 162. Okay? I would encourage you to try to pause the video if you want. Try this one on your own, and then we'll pick back up. But assuming that you did that, I'm going to just go ahead and fly through it right now. We have 1/3 times the square root of 72. That gives us 1/3. It's going to hang on the outside till we simplify the square root of 72. Square root of 72 can simplify down to the biggest perfect square factor is 36 times 2. Again, if you did not know that off the top of your head, you can use a calculator to figure that out. And another point worth repeating, it's worth using the square root of 36 versus 9 and 8, like 9 times 8 makes 72. But the square root of 36 will result in the least amount of work. If you did the square root of 9 times the square root of 8, well, now you're left with the square root of 8 that you have to break down again, as you saw up here, right? So the square root of 36 is 6, so I get 1/3 times 6 times the square root of 2. Well, 1/3 of 6 is 2, so that whole expression simplifies down to 2 rad 2, right? That term right there. This minus sign is just going to carry straight down like that. Now I have the square root of 162. Again, you can use a calculator to try and figure out what's the biggest perfect square that goes into 162. Maybe you could start at like, let's see, where would be a good starting spot? Maybe 121 if you were really unsure. 100's obviously not going to work, but 81 does. You wouldn't have to search for very long. This is 81 times 2 makes 162. The square root of 81 is 9, so you're left now with 9 square root of 2. And now, again, like terms in disguise, we see 2 square roots of 2 minus 9 square roots of 2 makes -7 of them. All right. Another really fun problem, if you want to try it on your own, I will not do it with you today, but I'd be remiss if I didn't write it down at least. Negative 1/3 times the square root of 90 plus 1/2 times the square root of 160 minus the square root of 10. See if you can work out that problem on your own. It's a great problem. The answer actually comes out to be 0, believe it or not. Super cool. So see if you can work that out and get that that whole big ugly mess of an expression is actually just equal to 0. Really cool. Really cool. So just a little quick recap for you. We talked about what a square root symbol means and what it does. We established this list of perfect squares, which I am imploring you to commit to your memory because it will be super useful, not just in Algebra 2, but beyond in other math classes and just in life. Like knowing what the square root of 100 is, that's probably a useful thing, right? This is why they're called perfect squares, because they allow you to construct squares, which is cool. When you're dealing with simplifying radicals, what you want to do for square roots is you want to find the biggest perfect square factor of a particular number. So I look here, what's the biggest perfect square that goes into 20 evenly? It's 4. What's the biggest perfect square that goes into 90 evenly? 9, right? And we did that for all of these types of numbers. It's always worth it to use the largest perfect square, as was seen over here, because it just reduces the amount of work that you have to do. If you pick 16 versus 4, notice one step and you're done. When you pick 4, you have to then deal with the square root of 12 again, and it just makes more work to get to the same spot, right? It's also required that you do pick perfect squares to make this work. If you just pick 2 random numbers that happen to be factors of whatever you're looking for, that's all well and good, but it doesn't help you get anywhere. It doesn't progress you anywhere, right? Like the square root of 20, I told you, you could certainly write that as the square root of 2 times the square root of 10. That is absolutely a true statement. It is not an incorrect statement, but it doesn't help you progress to any meaningful point. The point is so that I can rewrite this as this and not have to use decimals. That's really, I guess that's really the overall point of this, is to avoid having to use fractions and decimals to represent these values. We can represent them as nice, concise terms. All right. Second point we made was about adding and subtracting. When we have like radicals, we can add and subtract them together, as you saw here and here. Things that are unlike cannot be simplified. And these problems are some of my favorites that we do in Algebra 2 because they are exactly that, like terms in disguise. They don't look like terms originally, but when you actually simplify and simplify, you find, ooh, wait a minute, I can combine these two together and now rewrite them as one concise thing. I can combine all of these 3 things together and write them. I can combine these 2 together. If you work this out and get terms that do and don't combine together, well then clean it up as best you can. Combine the ones that can be combined and leave the ones alone that can't. Alrighty. Next time in class, we are going to talk about this. Oh yeah, that. What is the square root of -1? I'll leave you with that lingering thought for now. We're going to talk about that next time. Okay, so this is coming soon. Please try those practice problems if you get a chance. They are posted on Google Classroom. I would highly recommend doing them. They're always great practice. And next time we're going to learn about this weird specific case over here. There's going to be a lot to talk about, don't worry. Thanks everyone for your attention and focus, and I hope you have a fantastic rest of your day. Bye everyone.